For decades, data center thermal management relied on moving massive volumes of air across metallic heat sinks. In high-density environments, that air is now displaced by a dense, circulating dielectric fluid that physically encapsulates the silicon. This Venn diagram illustrates a critical reality. Purchasing an immersion tank does not yield a functional cooling system. True immersion cooling requires integrating 4 distinct engineering disciplines: thermal, electrical, fluid, and maintenance, into a single controlled core. We must engineer 4 interface domains: IT hardware, the immersion system, the facility thermal layer, and the building and people domain. The center boundary register dictates how these quadrants interact, explicitly handing off parameters like pressure limits, chemical compatibility, and total power. If these boundaries are left unowned during design, those gaps will immediately manifest as commissioning defects and thermal failures on the floor. Defining an IT load purely by its total kilowatt draw is insufficient for immersion qualification. A server described only by its top-line power gives us no actionable data about where and how that heat is distributed. We require an exact, granular IT bill of materials. As shown here, processors and memory dictate the local heat flux, the intensity of heat generated in a specific area. Board components, like specific network cards or unsealed relays, identify materials that might degrade when submerged. Selection is governed by 4 strict Open Compute project baselines. We must verify thermal performance and dynamic viscosity, which dictate cold starts and maintenance strip-back. Signal integrity metrics protect PCIe margins, while volatility metrics govern our fire and vapor control strategies. These interdependent variables require strict administrative prerequisites. This checklist shows you must secure sign-off on the IT bill of materials, fluid formulation, structural limits, and safety strategies. Notice the warning: equipment schedules cannot be released until these 9 inputs are frozen. Freezing these exact equipment and fluid combinations is the only way to establish a mathematically viable baseline for the entire mechanical design. This cross-section demonstrates the initial capture of heat inside a single-phase tank. Cold dielectric fluid enters at the base, and as it absorbs sensible heat from the servers, it rises through the middle flow lanes, driven by a combination of forced mechanical pumping and passive buoyancy. At the base, the cold inlet manifold utilizes balanced orifices. This precise physical distribution is necessary to ensure uniform flow and to prevent hot rejected fluid from recirculating back into the sensitive server intakes. Looking at these 3 architectural topologies, we see the transition from sensible heat to latent heat. Single-phase systems, relying on forced or natural convection, keep the fluid in a liquid state. 2-phase systems, on the far right, operate by allowing the fluid to boil, absorbing massive amounts of heat as it turns to vapor. 2-phase systems introduce unique engineering constraints. They eliminate the need for a dielectric circulation pump. Instead, vapor rises to a condenser coil, cools, and drips back down. This requires perfect vapor sealing and continuous, uninterrupted condenser availability to prevent pressure spikes. In either architecture, achieving a uniform bath temperature during testing does not mean the design works. System acceptance requires proving that the single worst-positioned component survives at the minimum allowable fluid flow. To move that captured heat out of the kink, we rely on the external hydraulic skid. This schematic shows the configuration of duty and standby variable frequency drive pumps, along with the specific mathematical formulas required to maintain the necessary volumetric flow rate. The heat then travels to the liquid-to-liquid boundary, typically a plate heat exchanger, or PHE. Inside this component, the hot dielectric loop transfers its thermal energy to the facility water system. The plates ensure absolute separation. There is zero fluid mixing between the 2 domains. The math governing this interface is exact. The PHE must be sized to absorb the total captured IT load multiplied by the fluid capture rate, diversity factors, and a strict engineered design margin. Let's run the calculation for a 1.20 megawatt single-phase pod. We start with the 1200 kilowatts of IT load and add the 20 kilowatts of heat generated by the pump itself. This gives us 1220 kilowatts entering the dielectric loop, which dictates a required mass flow of roughly 55 kilograms per second. We then run a pump input check and apply a 10% design allowance. This translates our total loop heat and flow rate into the final selection duty. The plate heat exchanger must be rated for at least 1.342 megawatts. The plate heat exchanger is the definitive thermal firewall of the data center. If you undersize it, you guarantee that thermal energy will cascade upstream directly into the IT hardware. This diagram shows the macro true heat balance equation that must be solved outside the building. Whether you use dry coolers or cooling towers, the total heat rejected must equal the captured IT load plus Kank auxiliary heat plus the facility water pump heat minus any heat reuse. You cannot assume the fluid load accounts for 100% of the data hall's energy. You must explicitly calculate the residual heat generated by dry zone components, like overhead power distribution units, network switches, and lighting, and ensure the room's ventilation handles it. This chart maps the 5-point temperature architecture. We calculate precise temperature approaches starting from the ambient outdoor peak, stepping up to the facility water supply, through the dielectric outlet, and finally stopping safely below the component's maximum junction limit. If your dry-only cooling infrastructure cannot meet that peak approach during tropical summer weather, the math forces a choice. You must deliberately engineer a higher facility water system temperature, accept thermal derating on the IT side, or install chiller trim to bridge the gap. Maintaining these temperatures requires mechanical redundancy across the entire heat path. Tier 3 designs provide N+1 capacity, allowing concurrent maintenance, while Tier 4 intent demands independent fault-contained paths where no single device failure removes critical capacity. Redundant mechanical components have zero value unless physical transition testing proves they can successfully isolate a fault and maintain end-to-end cooling capacity during a live failure. This schematic details the strict separation of control layers required to safely operate the system. The blue supervisory networks are utilized for workload optimization, analytics, and historical trending. The red layer consists of hardwired safety PLCs, providing local protective autonomy. Under no circumstances should critical safety trips, such as high temperature limits, leak detection, or fluid level alarms, be routed solely through a supervisory network. This diagram outlines the rigid 5-step maintenance custody loop. The central mandate is absolute. There are no open bucket fluid transfers and no wipe-to-waste practices permitted on the data hall floor. Once a server is powered down, operators must use a rated hoist to lift the hardware at a controlled speed. Strict drip-back timing and dedicated splash pans must be utilized to maintain total fluid inventory and prevent chemical contamination. Operational and maintenance discipline serves as the final engineering boundary. Any procedural error on the floor physically breaks the thermodynamic loop we just calculated. When catastrophic failures occur, such as a total loss of facility water flow, saturation pressures and component temperatures rise immediately. The response must be a controlled IT shutdown that leverages the dielectric fluid's thermal inertia, safely absorbing the heat rather than risking an uncontrolled fluid release. In two-phase systems, failures like condenser fouling or the accumulation of non-condensable gases create dangerous, localized pressure spikes. These require immediate sensor detection and automated isolation to maintain the pressure boundary. The primary rule of troubleshooting immersion systems: operators must stabilize the IT service using reserve capacity before attempting to localize the mechanical defect. Protect the thermal margin first, verify the system state, validate the sensors, isolate the domain, and only then correct the fault. Tracing the fault requires comparing live physical sensor data, temperatures, differential pressures, and leak indicators against the original engineered reference values to find the exact point of deviation. Troubleshooting must proceed methodically across the distinct fluid domains, altering only one controlled variable at a time to accurately isolate the root cause. Operational mastery means mathematically tracing the heat, enforcing strict hardware boundaries, and maintaining uncompromised thermal margins when the system is pushed to failure.